Intro music. Hello, everyone. Welcome back to the AAS YouTube channel. And this is in the ebook series, in particular, the new ebook, Common Envelope Evolution. And I'm very happy to have its authors with us today, Natasha Ivanova, Stephen Justham, and Paul Ricker. Hello, all.
Hello, everyone.
Good. I was waiting for Paul, but it's all good. Let's see. Today is my Thursday, May 27th in Phoenix, Arizona, and we've got the usual blue sky going. We're still relatively cool. We haven't quite hit the power switch hasn't been quite hit, and so we'll hit 40, 43 C here in another week or two. But Natasha, where are you at?
I'm in Edmonton, which is an Alberta, Canadian province. It's far north. It's a pretty province with Canadian Rockies. So I'm there and we have summer here.
Summer has hit. And Stephen, where are you at?
So I'm in Amsterdam. It's reasonably nice outside. It's been gray all day, but the sun's just come out and I feel more alive and awake already.
All right. Well, that's a good way to start. And Paul is coming and going with us as he's on his cell phone plan here. Where are you at, Paul? Okay, I'll answer that for Paul.
Lost in cyberspace, I think.
He's got his mute on. So I'll play Paul. Paul is in Illinois. Let's see, and if it's May, it's probably still slightly cool there in May. So I don't know if summer is quite hit yet there in Urbana, Champaign. So hopefully Paul will get his audio straight, and he's gonna keep coming and going. Okay, all good. So we have this ebook, Common Envelope Evolution. What gave you the idea to do such an ebook? Was there some meeting that you all met at and decided, oh, it would be a great idea to do this in a state of euphoria? Just what was the genesis origin moment for this ebook?
It's a little bit more complicated. It has very long roots yet to 10 years ago when we all met in Beijing. And it was a first Common Envelope workshop, which was organized by Stephen and me. And after that workshop, we wrote a big review paper on the Common Envelope Evolution, which was Common Envelope, where we stand and how to look forward and how to go forward. Mm-hmm. So that was kind of a beginning, because at the time it was only about a dozen of people in the world who worked on the Common Envelope. And we really wanted to have more people working. As time goes by and computers become a little bit more powerful, and also the importance of a Common Envelope Evolution for various events, including LIGO events, has become more obvious, more people wanted to move in. And at some point, I think AAS actually asked us about if we want to write a book on the same topic.
Cool.
And it took us quite a while to think about whether it was a proper time, because when we've been asked first time, it was yet too soon after the big review, and not much things have yet changed. And so it took a little bit of the time to actually start writing the book, to make sure that there was some progress, which will be reflected in the book. Although the book also was very different from what the review was about. The textbook, which is intended to bring a new generation of scientists into the field and work as a scoop, and also to give them a guidance. And I hope that Stephen or Paul will add up their view on how the book started.
Stephen, what's your view?
I agree with what Natasha said. So we were all in California in 2017 for a KATP meeting when Natasha started seriously discussing whether she should take up this offer from AAS Books. And I basically only agreed under the condition that Paul would also be part of this team, because I have respect for both of these people very much, but I felt inadequate to be only one of two writing this book. So I'm very glad that it was three of us. Not only because of the academic side, but also because last year during the pandemic, the three of us writing together was a
right.
Yeah, well, the three of us talking together was the highlight. The writing was maybe not such a highlight of my week, but actually the meeting and talking was good.
Very good. Paul, you with us?
Briefly. I mean, what I was able to get from Stephen and Natasha, yeah, the things started at KITP, and they needed somebody to write about numerical methods in particular.
Well, you seem like a good candidate for that. Very good. So let me ask then, so once you accepted the offer and it was a go, and this is just for perspective for, you know, younger people or older people who want to write an ebook, how long did it take from, okay, we're going to do this, to seeing it in print, let's say? So start to finish, how long was that process? 2 days, 2 weeks, 2 months? Where are we at?
It was closer to 2 years.
2 years. Okay.
But it was not a constant writing. It was initially was few months of kind of doing some drafts, working on what chapters will be, what will be in those chapters. Then it was a year of no work, and then pandemic has started, and we started to write.
Okay.
To some extent, maybe pandemic helped us because we've been
say.
encapsulated in our places with nowhere to go and no excuses to not participate in next writing meeting.
Very good. Very good. Yeah, that seems to be roughly a common time scale is roughly about 2 years to go from start to finish. You're the third ebook author who's made that comment. It took about 2 years. So it gives sort of the time scale for people. And let me just ask before we actually get into the book, since you may have other interests as well, what do you like to do for research? So let's start with Stephen. What do you like to do for research?
So I like to do anything to do with stars and stellar physics. So especially sort of in evolutionary timescale physics. You know, how do we explain the formation of the things we see in the sky, taking many millions of years to form these things and processes we don't see? It's kind of like theoretical archaeology, right? You see these things in the sky, how did they form and how many billions of years did they take to get there? I suppose especially compact binaries, so a binary that we see now that has a neutron star or a black hole or a white dwarf in there, and things that make supernovae, right? How do we get the variety of transients and explosions in the sky? But I'll do pretty much anything to do with stars, especially binaries.
Cool, cool. Natasha, what do you like to do for research?
Well, I love stellar physics as well, though maybe I like it on a shorter time scale than Stephen does. I like it more on the dynamical time scale. I like it on the thermal time scale. Okay. And I like to look at the extremes, like what happens if a star is smashed into another star. I was doing collisions. I love to do common envelopes. I really like to look what happens on the fast time scale and how the normal knowledge of stellar physics is challenged in extreme conditions.
Very good. We'll try Paul. Paul, what do you like to do for research?
So what excites me is fluid flows in a variety of contexts. I started life in galaxy cluster research.
And we lost him. Okay, we shall carry on. You back, Paul? Maybe not. Okay, onward we go. So this is going to bring us to this very lovely
evolution problems, particularly those involving dynamics and interacting binary stars seem like just a really fruitful area for investigation of in using
three-dimensional methods. I assume he was going to say there. Okay. Okay, Paul's going to come and go. Okay, common envelope involution, and this is a AAS IOP book. I love the cover artwork. Nice, nice palette of colors there. Matches the green background.
We should say Paul gets credit for that. It's one of his simulations. Yeah.
Very nice, Paul. Very good.
It's a special Google palette actually designed to replace Rainbow.
Oh, very good.
More.
A bit better in the Rainbow palette, no matter what it is. So very good. Nice. Let's see, let's just walk through this and then we'll get into it. So common envelope evolution. It's part of the SS IOP program. These are the corridors, 2, 4, 6, 8 corridors of the SS. That includes the education outreach. And in fact, I have this immortalized on my t-shirt. Those are 7 corridors of the SS. So I'm wearing the proper uniform to cover this ebook here. Steve Kowaller heads up the editorial advisory board, and Ethan Vishniak and Dieter are also on there, and a number of people associated with that advisory board. Common envelope evolution, IOP, and we get into it. So let's cover a little bit about what this ebook contains, what's it about, and its utility in education and in research. And so why don't we start off with sort of a broader picture, so some of the main phases. And I think, Natasha, you're going to cover that aspect.
Yeah, so I just want to say the idea behind the book. The idea was intended that the graduate student who at least took a stellar astrophysics course and knows stellar structure could understand now the physics of a common envelope event. So it is not the review of all the details possible, but we try to outline all the generic structure. So when they read the book and after that, people can talk to each other using the same terms. One of the problems in the field is that people can use the same terms, but mean different things. So the chapter, which is called as main phases, is partially devoted to that, to create the dictionary so that people will use the same words when they describe some physical phases. And here we start with outlining the main timescales which are involved into the common envelope event. And then we characterize the main phases of a common envelope event with respect to those timescales and the physics involved. So there are 5 main phases which we talk about this, and it's a loss of orbital stability, it's the plunge, it's self-regulated spiraling, it's a delayed ejection, and the post-common envelope evolution. So it is important because every single step and every phase should be modeled using different numerical tools. So when people discuss it, they have to use appropriate tools and appropriate timescales and so on. It's pretty bad when people mix up the numerical tools which are intended for improper timescale. So the main idea of this chapter to give this terminology and serve as the map for the book itself, because this is just the beginning. While we defined the phases here, then there are subsequent chapters which go into the further details for each of the phases. And those chapters are number 5, 6, 7, 8, and 9. So all the chapters which are devoted to the details of the specific phases. But this chapter is really important to be read first, so that can help people to at least find the chapter which is relevant to what they want to consider in their study.
Good. Good. Good, good, good. Very nice. Got some time scales here. Ooh, kind of like this one. We got at least the first 3 there for different masses. Orbital time scales, numbers 1, 2, and 3. Very good. I'm just walking through here randomly. Collision time scales. Okay, and then you get into each of the phases and talk about it. And it's a relatively short chapter here. There's the slow spiraling, termination of the spiraling, and then post-common envelope evolution.
Yeah, so here we kind of give the initial definitions and we give facts by like serving them on a plate. But then in the chapters which are related to each of the chapters, we go into details and more proofs of why is when.
Very nice. Good intro. Nice. And of course, this topic's taken on a huge life in the last couple of years. So this is super appropriate.
And if you can please go to the next chapter, because it's kind of important to look at that next chapter. Next chapter is related to the energy balance. The issue is that to this moment, the main way how the common envelope outcomes being characterized is by considering energy balance. In principle, what is done is you consider the state of a system before the common envelope, the state of a system after the common envelope event, and then you try to make a shortcut between those stages by assuming that the energy is fully conserved at the start and the beginning. That approach has a deep physical meaning, but it also has some problems because, for example, it implies that the common envelope event has to happen on a very short timescale, on a dynamical timescale. And also it cuts out lots of possible energy sinks or energy sources. So in this chapter, we have analyzed this commonly used energy formalism. There's a problem with the energy formalism, but in addition to that, we also had to define what exactly is coming into the energy formalism. And we listed here all the energy sources and energy sinks which participate in the common envelope event. And it also makes a foundation for the future discussion whenever we talk in more details about each of the phases. Then people can read again about those specific sources or sinks. And at the end, we did a brief guide of the energy components. And if somebody indeed wants to do the energy formalism in a new way, in the proper way, then there's a huge list of energy components that in reality have to be used for various common envelope phases. But in general, we think that there is no such thing as a common energy formalism which can describe all possible common envelope events. It can be done for some specific types of common envelope events for the very narrow range of donors and companions where you can feed it in and get some parameter out. But in total, it seems to be a little bit hopeless to go with the energy formalism.
Okay. All right. Cool. Yeah, I like the way this is lay out all your terms here. Yeah, some discussion of relevance or importance. Very nice. Very good. Something like this has been sorely missing in the literature like this. So this is really nice. So that kind of lays out the main phases in the energy budget. And of course, these are real objects. People actually do observe them. And so maybe we should jump down to linking with the observations. And Stephen, I think you're going to cover this part.
So you said you wanted a bit of a human touch. And I think a nice connection here is that the first time Natasha and I seriously interacted about research was about a couple of papers that we wrote where there's a population of things in the galaxy, the black hole low mass X-ray binaries, where people doing population calculations had said, that's fine, we can make these things, right? No problem, we can make these things if we take the energy formalism, assume a particular set of parameters, and they fall out. It's perfectly fine. And Natasha and I said, well, hang on a minute. If you look at the best estimates for what these parameters should be or the stellar structures, is that really a good way of explaining it? And I don't know whether our papers are correct, but it's not enough to assume this energy formalism and say, just because for one set of parameters we can explain some things we observe, that means that the description of the physics is true.
Correct.
Right. So I think up to this point, we all agree. Then the problem comes if you have a physical situation which is too difficult to be sure you can simulate accurately by brute force. You know, the arbiter of ultimate truth in science is connecting to observations. But then how do you infer from these observations whether you've got the descriptions of the physics right? Right? So if we can't trust these energy formalisms that people have been using. And we need to get from the observations whether we know we're correct. How do you do that? And this chapter is an attempt by, well, theorists, I suppose. So there may be observers in the world who have strong opinions on this, but trying to say, being honest, trying to be fair, with the observations that exist, how can they be useful to try to constrain the physics we want to understand? Now, you see there are 6 sections. The first is just a broad overview of something like what I've said. We have these observations. How do we use these observations in principle to compare to what we want to know? This section 10.2 is saying we have some systems that we think are post-common envelope binaries. Right? So they're systems that our best explanation is qualitatively that they've passed through this phase that I think we haven't even defined today, this common envelope phase. Our best guess is they've passed through this phase. What can we learn from that? Now, one of the problems historically has been that people have taken this energy formalism, which a lot of the book tries to hammer into people that we shouldn't trust too much, even though it's convenient, and fitted parameters based on that energy formalism and said, we've learned something. And we've learned something, but we may not have learned as deeply about the physics as you would want, because we're fitting to a parameterization, which is a step away from the physics. Right? Nonetheless, those systems exist, and we can learn something from fitting the parameters of those systems, right? From observing what we see. Now, one of the nice things is we have these post-common envelope binaries, and I mean nice in the sense of this makes life more complicated, which is often my definition of nice, right? We have systems which are supposedly post-common envelope binaries, and they get wider and wider and wider. And you say, oh, that makes common envelope evolution more efficient in this energy formalism sense, right? A wider post-common envelope binary means that our energy is used more efficiently, which Natasha would want me to say more precisely, but for today, let's be okay with that. And then at some point they get so wide and people go, this definitely proves that the common envelope efficiency is this much, or recombination energy must be used or something. Right. But at roughly that point, they become wide enough that they could be made by a stable mass transfer anyway. So there are alternative ways to make these systems that look like they could be post-common envelope systems. Okay. So understanding the inference from what we see is complicated. And you see there's 10.2.1 and 10.2.2, which are different ways of looking at the constraints, right? So some people have taken individual systems and tried to do these comparisons with what the models might predict or tried to fit the parameters. Right. And then of course you can do that on a population scale as well. But we have lots of these systems. Hopefully that kind of averages out some of the uncertainties. But then if you're comparing with your population models, then you have all these other implicit assumptions in your population models anyway. Right. Something which people often forget being the stability of mass transfer. Right? So when do you even enter this common envelope phase at all anyway? Right? Which is something Natasha put a lot of work into getting people to think about over the past decade. Indeed. Right? Just because some assumptions we made a long time ago about when mass transfer becomes unstable, just because it was written down 20 years ago, 30 years ago, it doesn't mean it's actually a good description of when it happens.
Epicycles comes to mind.
Yeah, but it's difficult. So when I was introducing myself, it's this interesting question that we see these outcomes of evolutionary processes that take place over timescales that are far too long for humans to wait around and observe. And we have a whole chain of these things, right? First, the binaries evolve into contact, and then you get mass transfer. Then the question is the mass transfer stable or not? And if it's unstable, is the envelope successfully ejected, and what do we see, right? And all these little pieces come into the inference. And if you just try to say, think about one of those in the chain, you may be misled because you're getting something else wrong. Now, my obsession, 10.2.3, is a little section, but it's one that I think not enough people think about. So there are a small number of systems, Natasha's laughing at me. There's a small number of systems where it looks like the envelope of both stars were ejected simultaneously. Right? Okay. So you enter common envelope, and the envelopes of both stars will went at the same time. I think that's really cool, but not enough people think about it. There's a double subdwarf system that is one of my favorites. So it was actually proposed in the mid-90s by Jerry Brown, because in the mid-90s we were worrying that hyperaccretion would turn neutron stars into black holes if neutron stars went through common envelope evolution. Right. but there are these low mass helium stars which seem to be good evidence it actually happens in reality, whether or not it's important for the double neutron stars that we observed at kilonova.
There we are. Sorry.
You're trying to jump back to.
Yeah, sorry about that.
That's okay.
Doing some exploration in the ebook.
Okay, so I've talked a lot about my favorite things. Then post-common envelope planetary nebulae. So one of the things I'd completely forgotten until I started going back and reading the old literature is that even in this Paczynski paper that is commonly cited for the starts of common envelope as a field, a subfield of astrophysics, he says, if we detect a close binary central star in a planetary nebula, that'll be really good evidence for this theory that I'm proposing, this mechanism I'm proposing. And I'd completely forgotten he said that, but he's a smart guy. And then later on, people come back and found close binary central stars of planetary nebulae. Right? And of course, people have both wanted to use those close binary central stars of planetary nebulae, that's a mouthful, I haven't said it so many times before, to try to infer things about common envelope, but also people have tried to use it to talk about whether they can explain the morphologies of the planetary nebulae, whether these interactions of the binary stars in the planetary nebulae affect the morphologies. Right. And actually, Natasha deserves a credit for finding some really nice papers about very early observations of things that are presumed to be nascent planetary nebulae. So very soon after the envelope was injected, even before really a lot of the ionization has gone on. Right. So that's probably the closest we can connect between the observations and the models that Natasha and Paul run, is these planetary nebulae really close after the injection, like within 100 years, a few hundred years, as ALMA observations.
Okay.
Some really beautiful images. If you jump to page 1015, so figure 10.2, or just the previous page, I think.
There we go. Yep.
Yeah.
Yep. Lovely.
Yeah, beautiful image. And you can see these outflows in the bottom right-hand corner, sort of a bipolar type structure. You can kind of see in the top that you have this blue stuff coming towards you and the red stuff coming away from you.
Okay.
Right.
Yes.
And maybe that was a post-common, like that's what a post-common envelope outflow looks like. Maybe it isn't, but we begin to get these observations, indeed, thanks to ALMA of the immediate aftermath of this thing. Now the next section, so 10.4 is another one that I think is important and is maybe not enough considered when people think about constraining common envelope evolution. So we don't just have the systems where the common envelope succeeded, right, where the envelope was successfully ejected and you're left with a binary star. We also have the systems where you went into unstable mass transfer, entered a common envelope phase and never came out again. You end up with a merger, right? Yes. And these weird, unusual single stars, post-merger stars, those are fun too, right? And those are also an outcome of common envelope evolution. They're just not we define it as not successful, which is slightly pejorative to these stars, but they're also cool stars, right? So supernova 1987A, right? For
example, yes.
Yeah, for example, right? It's a really important set of systems.
Cool.
Yeah, we could talk about that. I could talk about that forever, but we must have time to talk about 10.5, right? So this is one of the reasons why common envelope has become such a big deal in recent times. It's not just the compact object mergers. It's because we're seeing, we think we're seeing them happen, right? So about the time of this meeting that Natasha talked about in Beijing, there was this system called V1309 SCO going on, which was a ogle contact binary that went into outburst. And it was really the cornerstone of proving that some of these stellar mergers can make the types of, I was using the word cornerstone without even consciously being aware that we use it as a subheading. To prove that these subtypes of observations, the transients that we'd seen, could be made by ejections from either stellar mergers or common envelopes ejections. Right? And so Natasha and I had a paper, what year was it, Natasha? 2013, I think. Oh yeah, the same year as the review article, right? Showing how these light curves could be very nicely explained from the ejections from mergers and common envelopes and some of the weird features came out very nicely, and the whole parameter space falls out really beautifully.
Nice.
And I'm really hopeful that in the next decade, once we get more of these transient surveys going, we're going to get a big population of these transients and really begin to constrain stuff observationally. Maybe a bit optimistic, but let me be a bit optimistic. It'll be fun.
Yeah.
And the last section, and maybe even more optimistic, right? So Natasha pointed out when she was talking about the energy formalism,
Yes.
that there's a common assumption that the common envelope phase is dynamical, right? So quasi-adiabatic, and that's implicit in the energy formalism. It might not be true. And the longer the common envelope phase lasts, right? So the longer the binary takes to spiral through the envelope,
Yes.
the more likely we are to be able to see some of these stars that are undergoing common envelope evolution. Right, so actually see things in spiraling in a red giant. And okay, I see you're giving the overview of the book again.
Yeah, I'm goofing off. Here we go.
Oh, it's okay. Yeah, there's some nice discussion in the end of ways how we might be able to identify some of these weird stars if they're actually going through a common envelope. And if we did that, that would be just fantastic. That would really help a lot. So even if we're not observers, I think that there's a lot there in connecting real observed things we see in the galaxy with these models and trying to constrain reality from what we see. And yeah, it's all good fun.
Very cool. Very cool. So we got the sort of an overview, the evolution, the energy budgets, linking ideas with what's real on the sky. And of course, in the other one, we do models of various forms from 0D to 3D. And this is primarily the topic of section 4. And to the extent Paul is with us, I believe you're going to do section 4, Paul?
Sure. I'm not sure if you're going to be able to get much in the way of coherent answers from me, given that it keeps cutting out every 5 seconds.
We'll give it a whirl and see where it goes.
Okay.
I guess our 5 seconds was up.
I may step in and introduce, I mean, it will be not as good as Paul will be doing that, but there is a generic idea. So first of all, we need to consider what kind of physics we need to solve, which kind of equations we needed to include in the codes, which we will later be using. And I mean, equations over hydrodynamics is something that is obvious, and gravity is something that is considered to be obvious. But some things are not considered to be obvious and not usually included in 3D hydro codes used everywhere. For example, diffusive transport. That relates, for example, both to radiation, to transport energy by radiation, and also to convection, which may play a role, especially if a common envelope event is not taking place on one dynamical timescale. The energy still can be transported by convection from interiors to the exteriors, and it can be kind of significant energy loss. Later on is we also should take into account the equational state may play a role. Standard 3D code will use gamma law equation of states.
Ouch.
However, what is happening in the common envelope event is that the envelope is extending from a fully ionized zone to a fully neutral zone. So you have to encapture all those transitions from ionized states to neutral states. And that is even not talking about the transition to molecules, which may have taken place as well, right? Also, we need to take into account accretion. Right, so some equations which are related to accretion also need to be taken into account, and there are other sources of complications. The second point is that there are only limited number of types of numerical codes that one can use. And most obvious are smooth particle hydrodynamics and mesh-based codes. And there are also some transitional codes between them. However, each of those codes have their own pros and cons. And so in this section 4.2, we analyzed the codes. And then in 4.3, we analyzed the intrinsic errors which can be attributed to each type of the code. Specifically, for example, if the phase which you're dealing with has to conserve angular momentum at a high degree, maybe mesh-based code is not your favorite,
Right.
and so on. So you need to evaluate which phase you model, choose appropriate code, and understand what kind of errors will come out. So this is the main idea of this chapter. But of course, it is way more detailed than what I said now.
Good.
I think Natasha covered it pretty well, the parts that I was able to get. I think the diffusive transport is in particular is an area that has been underappreciated in simulations so far.
I do not at all claim to be an expert in this, but I really enjoyed going through this with Paul. He's really an expert in this. And we have this whole section on what can be trust and how do we think about whether the simulations that ran make sense, right? And yeah, I think that's wonderful. It was enjoyable whether or not you care about common envelope, to be honest. I greatly enjoyed that.
So let me ask a question, since you mentioned angular momentum transport and conservation or not thereof. Do we ever see any evidence or take into account in the models, since they're rotating magnetic fields? Got an partially ionized plasma. Do we get any Zeeman splitting, for example, from observations of common envelope? And is MHD important for a common envelope?
I do not recall any Zeeman splitting being recorded for pre-outburst moments.
I don't either. I'm just asking, but because I'm
during the outburst, it's not really likely. So, I mean, the layers which are getting ejected, they don't have much of a specific angular momentum. I mean, at least, I mean, not so much that not so much of a magnetic field generated by rotation that you can observe a Zeeman splitting, I believe. But in general, role of a magnetic field has been discussed, at least within one group, I believe Rochester group, who work on this. But I also believe that to the moment, it was not found to be very significant. Okay. Now, in general, saying that, common envelope is still in the very, very developing phase, right? And some exotic things which are still discussed, how they've been made and how they affect, are jets. And there could be a role of a magnetic field on developing of jets during the common envelope event, and that could help to eject some envelopes. But again, this is all yet in a developing state, and there is no really strong foundational research on this.
And that, of course, was sort of the leading question on my part. So where do you think we go over the next, let's say, 5 years or so? Either observationally, right? We're going to have a whole slew of new telescopes coming up over the next 5 years. And JWST will be coming up. Vera Rubin Observatory will be coming up. There'll be some new high energy telescopes coming up. People investigating different models. So where do we go science-wise with this topic, do you think, over the next 5 years? And the loaded question for all of you is, in 5 years, will there be a common envelope evolution 2? Whoever wants to go, take it, start.
Okay, I will do the first. I think with new transit surveys and so on, the first thing which will be really hard is to creating light curves. Now, it is very hard business to create proper light curves from common envelope simulations, but it will give us very important links between how common envelope proceeds and what we observe. So maybe, hopefully, if we will be able to create light curves in a good way, we can do some constraints on the common envelope physics. Okay. That's the biggest hope. Whether it will take 5 years or 15 years, it is not clear, but it's definitely will be the next hope. Along with that, people now do better and better simulations. I mean, now we have full common envelope ejections, and 10 years ago it was a no, right? So it is already a big progress. People also work on putting very massive and luminous stars into 3D 10 years ago, it was no, not possible. Only low mass stars, low mass donors being in a 3D. So there is definitely progress which will be observed in the next 5 years in simulations of ejections themselves, which may provide future clues on whatever alpha formalism, I mean, basically on the outcomes, especially for important systems with massive donors. So there will be definitely a progress. But whether it will be a common envelope book 2.0 with me as an author, in the next 5 years, I think no. Definitely not in the next 5
Longer
years.
time scale. Dynamical time scale, a little bit longer, maybe a thermal. Very cool. Stephen, Paul, any other comments on where the field should be heading over the next, or will be heading over the next, let's say, 5 years?
I would have said the transients. I would have started with the transients, the same as Natasha. I think that's going to be the exciting part.
Yeah.
Both, as Natasha said, because of the simulations and the observations just coming together at the right time. If I want to add something else, optimistic, maybe the galactic observations of the binary population will help a bit. But again, we have this question of how do you infer what you see, right? So we get the Gaia binaries in the near future and SDSS5 and maybe, but yeah, the transients is where we get the excitement, I think.
Cool.
Yeah, I'd agree with that as well, and especially to note the Gaia transients. Yeah.
Okay, and I'm sure people are going to continue doing the 3D models of these. Natasha mentioned that a little bit, particularly as these codes begin to parallelize across, thousands of processors or GPUs or something along those lines. As one progress in the.
Well, so there's some interesting developments in that regard. This new code OctoTiger
that I believe comes out of Clemson, if I'm not mistaken, Manos. I think that's right. Okay.
Can you hear me?
Yes.
Okay, so the group in Australia that has recently developed, it's a GPU code, and I think given developments in computer architecture, you're going to see a lot more of these codes that are designed for hybrid or heterogeneous parallel architectures and high concurrency.
Paul, let me ask you a question, right? Because it's still true that the dominant 3D codes are explicit. They're moving around on sound speed timescales. Do you see envisions toward moving toward being able to evolve on thermal timescales with 3D?
Well, I think that's certainly necessary for studying the later stages. I mean, places where the shocks start to become less important, and so yeah, I'd agree that there's a potential role for that in the later stages of common envelope evolution.
Okay, well, I have an idea. Then the students that you are now teaching common envelope evolution, those students will write common envelope evolution 2.0. So what comes around goes around. Very good. All right, that will do. Natasha, Stephen, and Paul, I want to thank you very much for spending some time and walking us through your really lovely ebook. Thanks. And everyone, that will do on this one, and we'll see you on the next one. Bye-bye.